So we talked last time about the fact that we can solve any problem in calculus or in math in general in three ways, right? Graphically, algebraically, and numerically. Last time we talked about the graphical and the numerical methods. Today we're going to talk about algebraic methods, all right? So let's talk about some properties of limits. So the way limits work is if you have something like this, the limit of f plus g, you can separate them. You can find the limit of f plus the limit of g separately, okay? So for example, if you want to find the limit as x approaches 3 of x cubed plus 5x, you can find the limit as x approaches 3 of x cubed, and then you can find the limit as x approaches 3 of 5x independently of one another, and then just add them to each other. Okay, so that's pretty much all that means. It's the same with subtraction, and it's the same with multiplication. So if you have a scalar being multiplied to a function, so if you have like 3 times x squared, you can find the limit of x squared, whatever it is, you multiply it by the 3. All right? And it's the same with, two functions being multiplied, divided, powers, and roots, and so on. All right. Let's put it to practice. Okay? So basically, here we have to find the limit as x approaches 4 of this function. So you're not going to have to do this every single time, but for this one, let's just illustrate the properties. So what this says is this. Look, you can separate this. So you see how you have 6x squared? That's a 6 times a function of an x squared, right? So this is the same as 6 times the limit as x approaches 4 of x squared, Why can't I? Plus, now we're going to do this one. So that's negative 6 times the limit as x approaches 4 of x plus the limit as x approaches 4 of 3. All right? So basically, there were 3 terms here, and we're going to find the limit of each of those terms separately. So take a look at this first one. You have the limit as x approaches 4 of x squared. What does x squared look like? What does x squared look like? It's a parabola, right? I'll get you in a minute. It's a parabola. Awesome. So now, as x approaches 4, we know what the limit of that is, right? What would the limit be as x approaches 4 of x squared?
Oh, well, it would be
16, right? As x approaches 4, x squared would be going up to 16. So then this is 6 times 4 squared plus negative 6 times, okay, so if you just have an equation of an x, right, y equals x, what would be the limit as x approaches 4? 4. Plus, now here you have y equals 3. What does y equals 3 look like?
a dot or a line.
It's y equals 3, right? So as x approaches 4, what's y? 3.
Forever.
So it's 3. So at the end of the day then, this is just 75. Okay? It is kind of cool. All right, so here's what we talk about when we talk about limits. Okay? When we're looking for limits, you can classify what you want to find the limit of into 2. One is polynomial functions and rational functions. So what does a polynomial function look like? Is this, in example 1, a polynomial function? Yeah, that's a polynomial function. Basically, you've got exponents from 0 to 0 and up, and they're integer exponents, right? So if p of x is a polynomial function, then the limit as x approaches c of p of x is just p of c. What does that mean? What did I do? If I want to find the limit as x approaches c, what do? I just substitute c in there. Okay, that's all I need to do. So basically, I need to use direct substitution to evaluate the polynomial for x equals c. That's all. So up here, in example 1, we could have just plugged in 4 and have been done with it. Okay? Now, what if you have rational functions? Then you pretty much do the same thing. If f of x is p of x over q of x, right? Then the limit as x approaches c is p of c over q of c. So basically, you plug in c into the numerator, you plug in c into the denominator. But what's the one condition that must hold? What's the one situation where it doesn't work? C can be 0. It just can't make the denominator 0, right? Right. Q of c can never be 0. Okay, so if q of c is 0, then the limit cannot be found by direct substitution. And we've got all sorts of other ways to do that. Okay, so let's use direct substitution here to evaluate each of these limits. So here, this is going to be, we're going to put 2 in here, so it's going to be 2 minus 3, 2 times 4, minus 2, minus 15. So this is going to be negative 1 over 9, over negative 9. That's just 1 over 9. Okay? All right. Let's find the limit of root x plus 3 as x approaches minus 1. What am I going to do? Plug it in. And that's just root 2. Yes? All right. Let's do another one. Here, how does that work? The limit as x approaches negative 8 of x plus 6. Okay, you get an imaginary number, don't you? Right? So this is the square root of negative 8 plus 6, which is the square root of negative 2. So that's dne. Okay. Because we can't get an imaginary limit. We just can't get an imaginary limit. Okay, but why did it turn out to be dne? Because what does x plus, the square root of x plus 6 look like? Half parabola, you mean a square root.
But only half. So like
A square root. So, but where does it start? At negative 6, and it goes that way, yes? But where am I? I'm looking for the limit as x approaches negative 8. Oh my gosh, that's like barren country. There's nothing there, right? There is not even a graph there. So how could I find the limit there? Okay, so this is all fine, but it's sort of boring because, yeah, we plug in, oh my god, like we've been doing that since Algebra 1. Let's make it a little bit more exciting. Indeterminate form. Okay. When direct substitution results in 0 over 0, all right, we call that indeterminate form. So what does that mean? Okay, so 0 over 0, that's not something that we can wrap our brain around, right? It's called indeterminate form because it's impossible to determine the limit of a function when the denominator is 0. So when the denominator is 0, I can't find I don't know what the limit is. In such a case, we have to use other methods to determine limits. All right, so when you get 0 over 0, it's indeterminate. We don't have enough information to figure out what the limit will look like. So we have to use other forms. And there are two possibilities for the outcome. One is that the limit exists, okay? So you get like 3 or -2 or 1 over 2. The other option is it diverges into negative infinity or positive infinity, okay? So when you get indeterminate form, there are a couple ways that we can get around it. One is by factoring. So what we do here is, okay, so when we plug in -2 here, you get 0 over 0, okay? So this results in 0 over 0, which means it's indeterminate form. So what we have to do is we have to solve this by factoring. Now, a few forms of etiquette. When you want to simplify an equation algebraically, at each step, you have to carry along this limit, all right? So this is going to be the limit as x approaches -2 of whatever is simplified here, okay? So we're going to factor this by grouping, okay? When we factor by grouping, from the left side, we're going to factor out an x squared, and we get x minus 3. From here, we factor out a -4, and we get x minus 3, which is nice because that's exactly what I wanted, over x plus 2. All right, so this is the limit as x approaches -2 of x squared minus 4 times x minus 3 over x plus 2. This is the limit as x approaches -2 of x minus 2, x plus 2, x minus 3, x over x plus 2. Okay, what happens now? What happens now? I can cancel out the x plus 2's, and now I can make the denominator go away. So yay, I'm not dividing by 0 anymore. Okay? So finally, this is equal to the limit as x approaches -2 of x minus 2, x minus 3. Now I can use direct substitution. And it is only at this step when I'm going to put in the value for direct substitution that I could drop the limit, okay, the LIM. So this will equal -4 times -6 times -5, 20. Okay, so that's the limit. So you see how we were getting 0 over 0, and we thought, oh my gosh, this is not cool. But then when we simplified, we actually got a cute little 20. Okay? All right, let's do this next one. Again, when you plug this 6 in, over 3 times 36 minus 66 minus 42, believe it or not, you get 0 over 0. Okay? So that's not cool. That's indeterminate form. So what I want to do now is I want to factor this. This is going to be the limit as x approaches 6, x minus 6, x minus 1, 3x plus 7, x minus 6. Okay? It is, I cannot give you full credit if you drop that LIM halfway, okay? Or at any of the steps. So the x minus 6's go away. I'm left with the limit as x approaches 6 of x minus 1, 3x plus 7. What am I going to do now? Now I can substitute. So I get 6 minus 1 over 18 plus 7, and that is 1/5. Isn't that cute? Yeah, it is. Okay, so that's one way of getting rid of, getting around indeterminate form. So you have a polynomial function and a polynomial function. Another one is by rationalizing. So you see here, you've got a rational function, but you've got roots in there, right? So what you want to do is you want to rationalize, you want to get rid of the roots, Okay? All right. If we do plug in 25 here, you get 25 minus 25 over 5 minus 5, 0 over 0, not cool. Okay? Rationalizing is you're going to multiply by the conjugate of whichever part has the root. It's not necessarily always the denominator. It can be the numerator as well. So this is going to be the limit as x approaches 25, x minus 25 over root x minus 5. Now I'm going to multiply top and bottom by the conjugate of whichever one has the root. So in this case, it's root x plus 5, root x plus 5. Okay. And I always, every year when I do this, I just get carried away and I start, to distribute the top. You don't want to do that. Okay, this is a lot simpler than you think. Now, what happens in the denominator? When you have a minus b, a plus b, it's going to be the first one squared. I just lost points. Yeah. So in the denominator, it's going to be the first one squared, which is an x. The second one squared, which is a 25, minus in the middle. Did I do that correctly? Okay. The top, leave it as is. Don't start multiplying things, even though I know it's so much more fun that way. Okay, what now? You cancel the x minus 25. So this is just the limit as x approaches 25 of root x plus 5, which is equal to 10. Okay? No. The second you plug in the actual value, you skip it. Okay, so let's do this one. Again, we're going to get 0 over 0, right? Because it'll be 2 minus 2, 0 over 0. So how are we going to rationalize this? What do we multiply by? 2 plus root x plus 4. So that's what I was trying to say before. It's not always just with the denominator. You have to rationalize the term that has the root. Okay? Yeah. So this is the limit of, okay, so the first, the top, I have what? 4 minus x plus 4. You multiply the one that you're rationalizing, not the other one. So here it's just going to be x times 2 plus root x plus 4. Okay, so now watch what's going to happen. This is the limit as x approaches 0. What do I get on top? When I distribute the negative, it's 4 minus x minus 4, which is, well, it's negative x over x times 2 plus root x plus 4. Okay, what happens now? What can I get rid of? The x's. So in the numerator, I have a minus 1 over 2 plus root x plus 4. Now, can I plug in a 0? Negative 1 over 2 plus 0 plus 4. Negative 1 over 4. Right. As soon as you plug it in, you don't. When you really can't do any more algebraic simplification, okay? And when you know that you're no longer going to get 0 over 0, it's safe. Okay? Yeah. Okay, so let's talk about limits of a power function at infinity. Okay? So suppose you have x to the power of n. And you want to know what happens at infinity. Okay? Now, if you're looking at positive numbers, all right? So suppose n is even. All right? Suppose n is even. What does it look like? That or that, right? So when n is even, it's an even function. Both ends are either up or both ends are down. Yes?
Yes.
Okay. So suppose you have positive x to the n. And if you want to look at this at positive infinity, for the positive numbers, is it going to be positive or negative? Is it going to go up or down? It's going to go up, right? And what if you look at negative infinity? For the negative numbers, it's still going to be up. You see what I mean? Right, right. So if this function is positive, then they're both up. So if it's negative x to the n, then at both infinities, it's going to be down at negative infinity, right? Now, what if n is odd?
Oh, then they're opposite.
One is
positive, one is negative.
Right, exactly. Okay, so let's take a look at this. Now, what I also want to tell you is this. So let's evaluate the limit at infinity. Okay, now, at infinity, okay, so suppose x is 1,000,000, okay? When you have x is infinitely large, like x equal to 1,000,000, look at what you have here. You have 4x to the 6. That's 1,000,000 to the power of 6, right? How many zeros are in 1,000,000?
6.
To the power of 6, that's 36 zeros, okay? Compared to that, a mere million here is nothing, okay? Compared to x, so I can totally ignore it. Compared to infinity to the power of 6, so if I'm comparing, like if I have 1,000,000 to the power of 6, compared to that, 1,000,000 to the power of 5 is nothing. So you can totally ignore it, okay? Because if 1,000,000 to the power of 6 has 36 zeros, 1,000,000 to the power of 5 only has 30 zeros. So it's like it's 1,000,000 times less. Can you imagine that?
Yeah.
So at the infinities, you can ignore everything but the term with the highest power. Okay? What we call these terms are negligible. That's the term. You could just ignore them. Okay? So now you just have the limit as x approaches infinity of 4x to the power of 6. Now, this is an even exponent, right? Whatever number I put in there is going to end up to be positive. The coefficient is positive, so this is going to be positive infinity. Okay? All right, what about the next one? Huh? Yeah, it is easy. Okay, so what about the next one? I'm just going to take the term negative x cubed. So this is the limit as x approaches negative infinity of negative x cubed. Now, okay, cube. So now, if x is negative and I cube it, I get a negative value. But then you have a negative in the front, so this turns out to be positive infinity. Yes, I can. If x is negative and it's cubed, you get a negative number. But you also have a negative in front, so it makes it positive. Huh? It's not negative x cubed like this. It's negative x cubed. You just cube that one first. Okay. So this one, we're going to take 4x to the 5. So this is the limit as x approaches negative infinity, 4x to the 5. So now, a negative number to the power of 5 is a negative number, so this is negative infinity. Here, we're taking negative x squared. Anything squared is positive, but there is a negative in front, so it's negative infinity. I know. Okay, reciprocal functions. Reciprocal functions, when you have 1 over x, they have a horizontal asymptote. So at the infinities, they all go to 0. Okay? Now, okay, so same thing here. We do the same sort of deal. When you have rational functions, we take terms with highest degree in numerator and denominator. Okay? So, here we go. This is then going to be the limit as x approaches negative infinity of, what's the term with the highest degree in the numerator? That's just the 5. There is nothing else. In the denominator, what's the term with the highest degree? What's the exponent of the x? 1. What about 10? That's x to the 0. Okay? So now, what you're left with is 5 over x. This is a reciprocal function, right? Reciprocal functions go to 0 at the ends, right? So the limit of this is going to be 0. You can also think about it as, you have a variable in the denominator. As the denominator gets infinitely large, what happens to the entire fraction? Very, very small. So if you have 5 pizzas and you want to divide it among 4 people, you know, everybody gets a good amount of pizza. If you have 5 pizzas and you want to divide it among 1,000,000 people, everybody gets a very tiny amount, okay? So this is just 0. Okay.
That's for all of these?
Yep. It's as simple as that. At the infinities, only the ones with the higher powers take effect. So what term from the top are we going to take? Negative 3x squared. And from the bottom? So this is the limit as x approaches infinity of negative 3 over 5x. And what's that going to be? That's a linear function, y equals x, right? At infinity, where is it going to go? So at infinity, where is it going to go? At infinity, oh, negative. I didn't see the negative. Thank you. So it'll be negative infinity. Okay? We're cool? All right. What about here? Limit 7x cubed over 2x cubed. What is this? That's it, 7 over 2. I know! Oh my gosh, it's only 9:30. Well, this is going to take like 10 minutes. That's why I didn't do the homework before. Okay, so. Oh yeah, there's that too. I forgot about that. Okay, so we're good. Okay, so the width in millimeters of an animal's pupil. I know this is like very irrelevant information. It's actually kind of cool. So it's given by this. Okay, so this is the width of the pupil. You know how like the pupil dilates and contracts depending on how much light there is? So x is the illuminance of the light shining on the pupils. Okay? So depending on how much light there is shining in the pupils, that's the width. So now it says write a limit to describe the width of the animal's pupils when the light is at its minimum. Okay? So in this equation, which variable is the light? It's x, right? So when you want x to be a minimum, what's the smallest? So as x approaches 0, right? So what you want is the limit as x approaches 0 of this bit Okay? So now we're going to solve this. We're going to simplify this. Okay, so what this is the limit as x approaches 0. Okay? What's with all those negative exponents, right? So why don't we do this? 152 over x to the 0.45. Can we do that? Plus 85. And over 4 over x to the 0.45 plus 10. Okay? So this is the limit as x approaches 0. And what I want to do now is I want to do a common denominator on the top and the bottom. Okay? So the denominator here is going to be x to the 0.45 over, or under, whatever. When I do a common denominator, it's 152.45. You want to move closer? Okay. Is everybody okay with how I did that?
Yeah.
And let's do the same thing with the denominator. So it's x to the 0.45 in the denominator. Okay. What can I do to that x to the 0.45 here and here? I can cancel them out. So now I have 152 plus 85. Ah! Are we okay here? Okay. Now, what happens if x goes to 0? What happens as x equals 0? So what do we get when x equals 0? 152 over 4, which is equal to 38. And what are the units? This was d millimeters. Okay? Now, that's all fine, but look at what this says. Find the limit and interpret your results. So can we now, in an English sentence, okay, explain in words what this means? Because in calculus, that's all it's about. Yeah, where? Okay, so we plugged in 0 for x. So 0, 0, 0. So what is this now? Yes.
So what it's saying is that it's asking for the width of an animal people with the legs that's given them.
Right.
So you would say the maximum width of animals people with the.
Right. So as the light is dimmed and it approaches 0, okay, the width of the pupil approaches 38 millimeters. Okay? This is what I got. Well, we don't know what kind of, but we don't know, but it's not for a human. We don't, it's, okay. So as the illuminance approaches 0, the width, huh? The width of the pupil approaches 38 millimeters. Okay. Write a limit to describe the width of the animal's pupils when the light is at its maximum illuminance. So at the maximum illuminance, it's going to be the limit as x approaches infinity of d again. So do I have to do all those calculations one more time? No, I can just take the final version okay? So what happens here? What we're going to do, if this is the limit as x approaches infinity, we're going to ignore the 152 and the 4 because we're just going to take the terms with the higher degrees, the highest degree, so it's 85x to the 0.45 over 10x to the 0.45, which cancel, so this is just 85 over 10, 8.5 millimeters. Okay? So when the light is brighter, they dilate. Okay, so they cancel. It's like x to the 0.45. At maximum illuminance, pupils, the diameter of the pupils approaches 8.5 millimeters. So more than the, what was I going to say? More than the, like the physical answer to the problem, it's the wording that is important here. Okay? Like you have to be able to construct like coherent sentences and use as little pronouns as possible. So like not it decreases or it goes to, like, what is it? Okay? It goes to 38 millimeters. I don't know what it is. You have to be specific. Okay, so you remember sequences. I mean, how could we not? So here what we have is some sequences, and we want to find the limits. This will be a much quicker way for us to figure out if something converges or diverges, right? Remember we were like plotting points and stuff? So this will be a much quicker way. So let's just, to get the context here, when you write the sequence as a function, right? AN is written as a function. The limit of the sequence is the limit of the function. If the limit exists, we say the sequence converges, and then if the limit does not exist, we say the sequence diverges. So what we were doing in chapter 10 was, and I'm going to do that briefly here, is we were saying, okay, what is A1? A1 is 4 over 2, 2. What is A2? 4 over 5. What is A3? 4 over 10. What is A4? 4 over 17. Write it down, yeah. 4 over 26, right? And what's happening here? The numbers are getting smaller and smaller and smaller, and if you graph it, what is it going to look like? It looks like it's going to look like it's going to go down from 2, okay, further and further and further down. Where do you think it's going to approach? It's going to converge to 0. So that's what we were doing in chapter 10. And I'll be like, okay, yes, this converges. Okay, we're good. All right. So now we're going to see if it converges using limits. So what we're going to do is we're going to find the limit as n approaches infinity, right? At the, like, when you look at like a sub, I don't know, 5,200, right? So as n approaches infinity of 4 over n squared plus 1. Well, this is just the limit as n approaches infinity of 4 over n squared, right? And what happens if the denominator there gets infinitely large? It gets infinitely small and it goes to 0. And because the limit exists, this converges. All right? Questions? All right, let's do the same thing here. I'm not going to plug in values. That's just crazy. Okay? So let's find the limit as n approaches infinity of 9 over n cubed, n plus 1, 2n plus 1, 6. Okay, now what is the term with the highest power on the top? Huh? Okay, so it's limit n approaches infinity. So I want the 9, and then, yeah, n, and 2n. And, yeah, 18n cubed, yes. Over 6n cubed. Both of what? So we know the highest degree when the polynomial is multiplied out completely. And if we were to multiply it out, the first terms would give us those. All right? So this is the limit. As n approaches infinity, 18n cubed over 6n cubed, which is just what? 3. So does this converge? It converges because it goes to 3. Okay? All right, so that's homework.